This is a video from section 16.2. The directions say to evaluate the line integral where C is the given plane curve. This example is taken from the Stewart Calculus textbook, 9th edition. Let's take a look at problem 7. We're looking at the integral over C of x plus 2y dx plus x squared dy. And when you're doing line integrals, you want to be thinking all substitution all the time. And you want to be able to parameterize your curve that you're working with, essentially. And here, C is broken up into essentially two curves. One which I'll call C1, and one is C2. C1 is a line segment that connects the point 0, 0 to the point 2, 1. C2 is a line segment that connects the point 2, 1 to the point 3, 0. Okay? And notice the arrow. Notice in C1, the arrow points toward 2, 1. And in C2, the arrow points toward 3, 0. That's important. Okay? Now, the curve C can be broken up again into C1 and C2. C1 is the line segment from 0, 0 to 2, 1. C2 is the line segment from 2, 1 to 3, 0. And this is the traditional way to parameterize a line segment. So we're going to take the point xy and we're going to set it equal to 1 minus t times the initial point. In this case, the initial point is 0, 0. And we're going to add t times the terminal point, which in this case is 2, 1. T is restricted between 0 and 1. In other words, t is greater than or equal to 0 and less than or equal to 1. And if you notice, if I plug 0 in, the second term drops off, right? Because 0 times anything is 0, right? In this case, 0, 0. And you just get the origin. And if I plug t equal to 1 into this equation, I get the ordered pair 2, 1. And that's the terminal point. And if I plug in a value of t that is in between 0 and 1, I get a point that's on the line segment that's in between 0, 0 and 2, 1. Now, if we equate coordinates or components, right? If I look at x, that's going to be 1 minus t times 0 plus t times 2. So x equals 2t. All right? If I look at y, that's 1 minus t times this 0, the second 0, plus t times 1. So y equals t. Now I need a value for dx and dy. Now dx is 2 dt and dy is 1 dt. And so soon I'm going to take those values and plug them in for x and y and dx and dy accordingly. So I'll show you that shortly. Now, if we want to parameterize C2, it's going to be as follows. It's, again, another line segment. This parameterization, by the way, only works for line segments. That is crucial, okay? Now, xy is 1 minus t times 2, 1 plus t times 3, 0. And again, make sure you understand t is less than or equal to 1 and greater than or equal to 0. Okay? Now, x is 1 minus t times 2 plus t times 3. So again, x is 1 minus t times 2 plus t times 3. That's right here. Y is 1 minus t times 1 plus t times 0, or 0t. And so when I simplify, I get x equals 2 plus t, and y equals 1 minus t. dx is 1 dt. dy is negative 1 dt. Now, I'm going to look at the integral over C1. Remember, this is C1 right now, of x plus 2y dx plus x squared dy. Now, if we go back to C1, remember x equals 2t, y equals t. And so if you notice, I'm going to replace x with 2t. I'm going to replace y with t. So I get 2t plus 2t, and I'm going to take that quantity and multiply by 2, because remember, dx is 2 dt. And if you're wondering what happened to the dt, I saved it for the end. Okay? And then I'm going to add, I'm going to replace x with 2t, and I'm going to square it. And remember that dy is 1 dt. So we're okay. And then I'm going to take this and integrate with respect to t. And remember, I'm integrating from 0 to 1. So 2t plus 2t is 4t. So I get the integral from 0 to 1 of 2 times 4t plus, and now if I square 2t, I get 4t squared. So I get 2 times 4t plus 4t squared. And if we come over here, 2 times 4t is 8t, so I get the integral from 0 to 1 of 8t plus 4t squared dt, which is 4t squared plus 4/3 t cubed from 0 to 1. And when I simplify, I get 16/3. So you notice in a Calculus 3 class, the integrals, especially when you're doing line integrals, aren't too bad. It's the setup we have to really pay attention to. It's substitution. I can't stress that enough. Now, the integral over C2. Now, of x plus 2y dx plus x squared dy. Now, let's remind ourselves about C2. Remember, x here is 2 plus t and y is 1 minus t. dx is 1 dt, dy is negative 1 dt. So let's go back. I'm going to replace x with 2 plus t. Y is 1 minus t. So I'm going to take 2 plus t plus 2 times 1 minus t. And then wherever I see an x, I'm going to stuff in 2 plus t, and I'm going to square that guy. And then dy, remember, is negative 1 dt. So that's where that negative 1 came in. And don't forget, if x is 2 plus t, dx is 1 dt. So multiplying by 1 doesn't change anything. And don't forget, the dt got saved for the end. Now, on the next line, I'm integrating from 0 to 1 of 4 minus t minus, that's because of that negative, so it's minus 2 plus t to the second. It might be tempting to square out 2 plus t, but I claim that's not necessary. So I'm going to take the integral on the next line. So here we get 4t minus 1/2 t squared minus 1/3 times the quantity t plus 2 to the third. And I'm going to evaluate from 0 to 1. Now, I need to replace t with 1, and I need to replace t with 0 and subtract those results. Fundamental theorem, right? So when I replace t with 1, I get 4 minus 1/2 minus 9. When I replace t with 0, the first two terms drop off, and you get negative 8/3. So I'm going to get 4 minus 1/2 minus 9 minus negative 8/3. But that's negative 5 minus 1/2 plus 8/3. And if you don't mind, I just did a little arithmetic here and got negative 17 over 6. And I'm pretty much done. I take the integral over c of x plus 2y dx plus x squared dy. That's the integral over c1 of x plus 2y dx plus x squared dy plus the integral over c2 of x plus 2y dx plus x squared dy. And that's 16/3 minus 17/6, which is 5/2. And that's going to do it for this video for section 16.2, where we worked out problem number 7. And again, this is from the Stewart Calculus textbook, 9th edition. Thank you.